welcome everyone to our last two sessions of the second day of PyData Global Edition. My name is Jana. I'll be your host today, and it's such an honor to be here in this 2021 edition. Now I'm welcoming Niels. He is a machine learning engineering and current maintainer of Flyte, an open source ML orchestration tool, and author and maintainer of Pandera, a data testing tool for data frames. He has a master in public health with a specialization in social-medical science and public health informatics, and prior to that, a background in developmental biology and immunology. His research interests include reinforcement learning, AutoML, creative machine learning, and fairness, accountability, and transparency in automated systems. He enjoys developing open source tools for improving data science and machine learning practice. And today, he's going to talk us about robust end-to-end online machine learning applications with Flyte, Pandera, and Streamlit. Without further ado, the connections is yours, Niels.
Hi, everyone. My name is Niels. And today I'm super excited to talk to you about robust end-to-end online machine learning applications with Flyte, Pandera, and Streamlit. So before jumping in, a little bit of background. So on top of what has been introduced already, I'm a Flyte maintainer and author of Pandera, and I have various background in biology and public health, but now I've sort of gone through a journey in data science and machine learning, and I guess I've settled on this mission of making DS and ML practitioners more productive. So I want to start this talk with a bit of motivation behind it, and then dive in and distinguish between offline and online machine learning, and then highlight a particular case of online learning, which is weather forecasting. And then after that, I'll kind of do kind of a quick start of Flyte, Pandera, and Streamlit, all of which are the different projects, the different components that I'll be putting together for this particular machine learning system. Dive into the pipeline architecture of the online learning system, show you a little demo of what it looks like in the end, and then give you some takeaways. So online, I've been seeing this term full stack data science / machine learning engineer. And when I see this, I have to think to myself, what even is that? So I have to remind myself, when I started, I was really obsessed about the algorithms and machine learning training and all that stuff. But I realized that in real world ML systems, only a small fraction of that entire system is ML code. And there's a lot of tools and infrastructure surrounding it that support it in production. So just to remind you, maybe a little sketch of what that might look like deploying models to production. You start off in a research and development phase, collecting data, formulating problems, prototyping models, and evaluating in the lab how those models perform. And if you're lucky enough, and if you can prove or justify to yourself that the models should be released to production, then you might work with a DevOps or MLOps, as maybe it's been branded these days. You might work with a DevOps person to deploy the model, work with a front-end engineer to build a UI. You deploy it, and then your end users, be they internal or external to your organization, use that UI, and then you can use, if you put the right instrumentation in, you can use whatever that interaction looks like to evaluate models. And then, of course, there's the endless iteration cycle between R&D and production. So to begin this presentation, I want to start with this question of how far can a small data team get building and shipping production model-driven data products? And at least in my experience, this is oftentimes a small team, like 1 or 2 people, and if you're lucky, more with the particular specializations. And on top of this, I gave myself this challenge of building an online learning system that updates a model hourly and then displays forecasts on a web UI. And I want to focus on online learning because it forces the practitioner to think about how to manage incremental data acquisition, how to manage model updates in production as a first-class citizen, how to think about it in that way, and then how to evaluate models where the model only sees each example once. So I have accepted this challenge, and for the rest of this talk, I'll show you what the results are of this sort of exploration. But before that, just a little crash course on offline versus online, just so everyone, it's just literally a single slide. So offline learning is otherwise known as batch learning. So you have a static training data set. You train a model on that potentially with multiple passes through it. And then you deploy it if even, and you might refresh that data set and retrain. And so, it's up to you how often you do that. Whereas with online learning, it's kind of like the default setting is that you're getting data in at some relatively fast frequency. And I guess that also depends on the use case. But generally, the model only sees each training instance once in some temporal fashion. And so what are some of the reasons why online learning would be deployed? So if your data isn't static, like by definition, your data isn't static, it's generated as a function of time, or if your data might be too large to practically store or train a model all at once on, you might want to use online learning. Other reasons is if you just fundamentally can't assume IID data. So like today's temperature depends on yesterday's temperature. Or if your model needs to be up to date as possible due to the dynamic nature of the data. So all of these points are kind of interrelated. So the use case I want to focus on is weather forecasting, in particular hourly temperature forecasts. And we'll be getting our data from the National Oceanic and Atmospheric Administration using the Integrated Surface Data Set, ISD, which is various weather-related metrics like temperature, dew point, sea level pressure, things like that, collected at an hourly resolution, but the data isn't necessarily like updated in real time. So there is some cadence with which these data are updated. And the way you interact with this data is you make an API request to the NOAA API endpoint. The query or the request might look like this. You get a JSON response, and part of that response is metadata pointing to files containing the actual data you want. So once you have that, you request one of these CSV files, and you get the raw data in this format, CSV file. And in this case, we're focusing on this temperature column, which is itself a string that you need to parse. And that was one of the challenges, or one of the points I wanted to challenge myself with, is there are various weather APIs out there with clean data, but I wanted data in a fairly raw format. So now we have the data out of the way. We'll just use a very, very simple autoregressive model. So this is basically linear regression, where you predict the scalar value, temperature in this case, at time t, based on some bias and some coefficient, some linear combination of the previous time steps with, of course, the irreducible error. For full transparency, I actually included additional features, which are one-hot encoded time-based features, so day of week, day of month, month of year, etc., just to give the model a little more context. And the evaluation metric I use is similarly naive. Maybe I'm not a time series and analytics expert, so maybe some of you might be able to point out better metrics for this, but I chose exponentially weighted mean of the absolute error. And in this way, since we have an online learning system, we can similarly evaluate our model in an online fashion. So this is a kind of a cartoon sketch, high-level overview of the pipeline. In the this kind of empty gray box is the pipeline that's going to do our computation, all the heavy lifting, which is going to be done by Flyte, which is an orchestration and execution engine. And sandwiched between this clean raw data, you see these two green boxes. These are meant to represent the Pandera schemas, and I'll show you what that exactly looks like later. But these are meant to ensure that the data quality of data coming in from the external source, in this case, the Noah.gov API, is in the expected format. And then once we've cleaned and parsed the data, it comes out in the expected format that we need for training. After we prepare the data, we update the model to the latest time step, the latest available time step, get the forecast, and then our Streamlit web UI will read that output to display it to us. So before diving deeper into the exact pipeline, I need to just briefly introduce these three technologies, starting with Flyte. So Flyte is like the stratosphere. It has many layers, and it can mean many different things to many people. So if you're an infrastructure person, maybe it's a Kubernetes first workflow orchestration engine, which it is. Or if you're a data engineer, maybe you can see it as an automated data lineage tracking platform. But as an ML engineer, I particularly am interested in it because it's a type-safe data pipeline language. And so you write tasks which are isolated pieces of data processing or computation. And here we're using FlyteKit, which is the Python SDK for Flyte. And here we're decorating our two functions with the add task decorator. And what that does is you can think of it as a Docker container that wraps all of that code and then runs it somewhere in some arbitrary to be determined location. Here we're just transforming data and aggregating it. So like a simple toy example. And then you can compose workflows together, compose workflows by connecting tasks together. And so this looks like Python, but it's actually a DSL where this function body is compiled and into a protobuf format that Flyte can reason about. And all the types are important in that Flyte can analyze them and tell you beforehand at compile time whether your workflow is going to work or not, whether it thinks it's going to work or not. So you can, all the code you saw above, you can develop and execute locally. But then once you want to deploy and scale it, you send it over to a Flyte backend. So you give it your compiled workflow and some config. And Flyte is this abstraction layer that schedules and figures out where, when, and how to run it on a Kubernetes cluster. Flyte doesn't exist in isolation. You can use a whole suite of integrated tools, including Spark, PyTorch, TensorFlow, Kubeflow. And this brings me to Pandera. So when I joined the Union AI team, I integrated Pandera, which was a perfect fit because it is basically a data frame typing library. And so when typing started emerging in Python as this gradual typing approach, I was interested in like answering the question, scratching this itch of, I really want to type by data frames because they're like these complex black boxes of just data that I don't know what is in there. So Pandera essentially adds guardrails to your pipeline. So if your pipeline is this suspension bridge, data frames are the people traveling through it. It helps them not fall off and break your code. So Pandera started off as a pandas data frame library, but as it gained adoption, I saw the need for expanding it to other data frame frameworks. And so coming in the next release is, I'm happy to announce that we'll be adding support for Dask, Modin, and Koalas. And there are so many other libraries, emerging libraries out there that the next piece of work to do is to support like an easy way of extending it to other non-pandas compliant libraries. So with Pandera, you can encode assumptions about data frames as schemas. And so this might look like data classes a little bit, or Pydantic if you're familiar with that. And schema inheritance is followed here in that you can inherit from other schema models, and the fields that are defined in the parent classes will be present in the child classes. Pandera also supports indexes and regex column matching. So if you have fields or columns that are logically grouped together with the same validation rules, you can make very concise schemas. You can also extend Pandera's built-in validation checks. So this is checking if the field is greater or equal to 0. And custom checks are super easy. It's just a method in the class. It's also super easy to integrate with Flyte. You just have to install this plugin, and any add task decorated function will at runtime check the inputs and outputs of data frame schemas defined with Pandera. And then if something goes wrong, you get informative errors. So if a column is not present in the data frame, it complains. Or if a column has an unexpected data type. Or if your assumptions in the schema are violated. So like here, there's the presence of negative numbers and odd numbers. And if you provide this lazy equals true parameter, you see that this failure cases data frame inside this schema errors object provides all of the failure cases that caused the error. So it makes it super inspectable what exactly went wrong. And then last but not least, there's Streamlit, which is a delight to use. It's basically a way of making interactive UIs via scripting. So here's a Hello World app. You run Streamlit run myapp.py, and then you get a nice, beautiful web app for you to interact with. Streamlit and Flyte work well together. So Flyte has this notion of a client called Flyte Remote, and you can use this remote object to get executions, workflow inputs and outputs, task definitions, anything like that. And you can then grab that data and display it on a Streamlit app. Okay, so this is maybe the next few slides are the most involved. So I'll just remind you of this high-level overview. The actual pipeline in the end doesn't quite look like this. And that's because I set forth certain requirements when doing this project. So the first one is that it needs to support incremental model updates and pre-training. The second is that I don't want to waste request fetching data from the NOAA API. And the last is I want to implement online evaluation metrics, which I hinted at before. So it's a little more busy, but I'll talk you through it. Basically, the inputs to the Flyte workflow is this genesis date time, which is when the first ever run of this model will occur. And then a target date time, which is greater or equal to the genesis date time. So this is the thing that when you schedule this job to run, say every hour, this is a thing that increments. You have a look back window, which just tells you, okay, how many time steps back, in this case, at an hourly resolution, does your model have access to make the next forecast? And then how many days of pre-training do you want when you initialize your model at the genesis date time? So the neat trick that's happening here, you'll notice, is here's the get latest model workflow, and then here's the get latest model workflow here, but with the previous timestamp. So the mind-blowing thing here is that Flyte supports recursion. And what that enables is I can be very efficient about how I run my workflow. So when I first run this workflow, I'm going to initialize my model. So that's all fine and good. But once target date time is greater than genesis time, I'm going to try to get the latest model from the previous time step, which in the second run will be just this initialized model. So it's, recursion always kind of boggles my mind a little bit, but when you grasp it, this basically it's cached. So this little icon here means that the outputs of each of these pieces of computation are cached. And so it doesn't rerun that computation. It just grabs the latest model and then updates it. And then from there, we get our forecasts and our metrics, and then we plug that into Streamlit. But where's the data coming from? So this doesn't mention anything about the data. Well, we need to zoom in to initialize model and update model. So within this workflow, we're initializing the model in metrics, but then we're also getting the training instances and caching that within this workflow. And same goes for update model. And this way, we're kind of creating it's not a feature store, but it's kind of like a feature training data cache, where if we want to reproduce this model and reproduce this run, all we have to do is provide the same exact parameters, and we'll be able to recover the exact same model. With a caveat of if the node.gov API has somehow been updated, then it won't exactly be the same model. And then finally, with the model evaluation piece, we want to compute training and validation error in an online fashion. So this is kind of pseudocode that does this. So basically, before we update the model at any given timestamp, we feed, we do like we make a prediction given that model. And since the model hasn't been trained on it yet, this is validation error, right? Then we update the model here, and then boom, right in the same place, we're gonna feed the same training instance, but now that it's seen it, it's technically the training error. So in this way, we can, in a single, with a single piece of single pass through a single training instance, we can compute a running validation and training error. And then finally, really quick, I just want to show you what this looks like when we connect it all together. So you can actually go to this bit.ly link. The presentation slides will let you get here really quickly, but just want to show you the interactive element here of I've pre-run a bunch of different workflows for different locations, different cities, and these happen to be cities where Union AI team members reside. So they can use this to make clothing decisions based on the temperature forecast at their risk. But as you can see from the model metadata, the model is not great. So the model is mean absolute error exponentially weighted is like 7 degrees Celsius off, which is pretty bad. But that said, this is where you iterate on that one piece of the ML system, right? And then finally, I just want to show you the Flyte console. So this is literally all the executions for all the different workflows. So here's the Seattle workflow. Here's the Green Bay, Wisconsin workflow. And here you can see, you can go in, you can look at the execution graph. It looks sort of like the graph I showed you before. You can inspect the inputs and outputs of each of the nodes in this graph. So it's really quite easy to audit, what exactly went wrong if one of these pieces fail. Jumping back here. I'd like to conclude. So, this is fairly obvious, but I think we should move towards full stack data science ML engineering teams and not individual people, although you might find yourself in that situation. And I want to just emphasize that I've presented to you 3 tools that lets you execute and orchestrate computation and scale it, add types with Flyte, and then add type safety to your data frames or data frame-like objects with Pandera. And then finally, make really nice interactive UIs with Streamlit. And with that, I will open it up to questions. I'm happy to answer any questions you have. Here's my contact and a bunch of links to the weather forecasting app, the repo, and the 3 projects that I've showed you today. Thank you.
Thank you. Thank you so much. And we have some questions, actually. Let me read for you. Alexander is asking, what are the difference between Flyte and Cloud Composer?
Oh, I'm not super familiar with Cloud Composer. So I am aware that there are a lot of DAG-based ML or data processing ML orchestration tools out there. I know somewhere we've done a comparison. I think there's a blog, or we're working on a blog. But sorry, I'm not knowledgeable about enough about Cloud Composer to answer.
I think so, yeah. Of course, always we can move to the talk to continue more discussions, but yes.
Yeah.
Ali, sorry if I pronounce mal your name, is asking, what is the main difference between Flyte and Airflow?
This I can say a little bit more about. So the history of Flyte is that it was started at Lyft. And actually the team that built Flyte initially built it on top of Airflow. And I need to get my story straight here, but essentially they found certain requirements that they had at Lyft that was not fulfilled by Airflow. I can get back to you, Ali, about that, what those specific needs were. But they determined that, okay, we'll have Dockerized tasks and orchestrate it with Kubernetes. And I haven't used Airflow before, but I'm not sure if the back end of that is Kubernetes. You can correct me if I'm wrong. But that's the main differentiator of Flyte. Is that it's Kubernetes first, and so it's basically an abstraction layer on top of Kubernetes that abstracts away a lot of things, a lot of configuration, a lot of scheduling, things like that, and adds a few more little pieces of functionality that Kubernetes does not offer.
Okay, thank you. Alex, is Pandera like I'm not sure, Pandatic or Pandatic or Pandentic,
yeah.
but for data frames?
Yeah, yes, exactly. So I think the two projects, I think Pydantic is slightly older than Pandera, but that's pretty much exactly right. So Pandera's original syntax, which is still supported, is more like object. It's like a dictionary of keys and columns. But then a contributor made a Pydantic-like interface. So now it looks very much like Pydantic. And then in actually the next release, it's going to be a valid Pydantic type. So you can use it in your Pydantic models. Yeah.
Okay, and I will finish with this just because the hour. To Alex, yeah, it's from Alex. To what extent is Flyte a perfect alternative?
Yeah, so Prefect, we are very much aware of Prefect. So I need to, again, educate myself more about this, but I think from my understanding, Prefect's backend is Dask, and Flyte's backend is Kubernetes. So in a sense, and Flyte is built to be language agnostic. So if your container contains any language's code like C or R or Julia, you could use the Python SDK and point to that image and give it some inputs, and it would work in your workflow. So Flyte is if your team or if you are familiar with Kubernetes and you want to take advantage of that, then Flyte Flyte is the logical choice. But I don't know too much about Prefect and the advantages of Prefect, so I'd be curious to learn more, though.
Okay, thank you very much. We have still 3 more questions. So kindly invite you to go to the Talks channel. I will stop the record, and thank you again so much for this nice presentation.
Thank you, Diana.